Mechanical and fluid systems both vibrate. An example of a mechanical system is this slinky. If I shake one end, I can set up a vibrational mode. The corresponding type of modes in fluid systems are called acoustic modes. Penny whistles and slide whistles take advantage of different types of acoustic modes to create music. In acoustics, as in vibrations, the motion of molecules is the result of waves propagating through the material. In the case of a tube full of fluid, waves produced at one end of the tube can reflect off the other end of the tube and move back towards the source. The interaction between the waves can create what is called a standing wave. This animation shows how the left and rightward traveling waves interact to form a wave that appears simply to move up and down at any given point. Since waves are caused by reflections and transmissions from boundaries in the fluid, the shape of the standing wave changes if the boundary conditions change. This change in boundary conditions is the difference between slide and penny whistles. Now let's talk about some terms used to describe standing waves. A system mode is a response that the system really wants to provide. You can think of this as a resonance condition, where you can provide relatively little input energy to get a big response. This is an example mode shape of a vibrating string. What's being shown here is an envelope of the string deflections. The displacement of the string is fixed at both ends. These points here and here are not moving. They're called the nodes. These points here, here, and here have relatively large deflections. The string's moving a lot from the left to the right at these points. These are called the antinodes. The wavelength of the standing wave is one complete period of the signal. Modes are commonly specified by the total distance relative to the wavelength. For this particular mode, the length is 1.5 times the wavelength. This would be called a 3/2 wave mode. Fluid systems also respond in particular mode shapes, just like string vibrations. As my first fluid example, let's take a look at this open-closed duct. This name reflects the fact that one end of the duct is open to the room and the other end is sealed. These impose boundary conditions on the behavior of the pressure and the flow velocities at the ends of the ducts. Air can flow in and out of the duct from the room at the open end of the duct, so I have a non-zero velocity V sub u at this end. The room is large enough so that flowing a little of that air into or out of the duct doesn't affect the room pressure. So the pressure at the open end is the same as the room pressure. It's fixed. No fluid can flow into the closed end of the duct, so the fluid velocity V sub d is 0. I have a boundary condition on velocity at this end of the duct. The pressure here is unspecified. I can push as hard as I want against this end of the duct without affecting the velocity boundary condition. The lowest frequency mode that satisfies these boundary conditions is the quarter wave mode. In this case, the wavelength is 4 times the duct length, so the duct length is 1/4 of a wavelength. The shape of the pressure mode is in blue. There are no pressure fluctuations at this end, and the fluctuations are maximized at the closed end. The shape of the velocity mode is complementary to the pressure mode. The velocity is 0 at the closed end and maximized at the open end. The pressure and velocity describe different types of energy in the fluid. Increasing the pressure compresses the potential energy of the fluid. The fluid velocity affects the kinetic energy. Kinetic and potential energy are traded back and forth along the length of the duct. When the kinetic energy is high, the potential energy is low, and vice versa. This is the next highest mode of the duct. It's a 3/4 wave mode, since the length of the duct is 3/4 of the wavelength. Again, the pressure mode is shown in blue and the velocity in red. Both modes satisfy the boundary conditions of no pressure fluctuations on the left and no fluid velocity fluctuations on the right. A slide whistle acts like an open-closed duct. The fipple end acts like an open termination. The slide moves a piston that doesn't allow any flow, so the other end is closed. Moving the slide back and forth changes the length, which changes the wavelength of the standing wave in the whistle. The changing wavelength causes the whistles to resonate at a different frequency, which changes the tone of the sound. For example, with the slide in this position, the pressure mode is as shown here. The wavelength is long and the pitch of the sound is low. If I move the slide into the whistle, the wavelength shortens. This corresponds to a higher frequency and the pitch of the sound increases. This is the open end of the slide whistle. The gap is called the fipple. When you blow into this end, the fipple causes pressure fluctuations. These fluctuations have a lot of different frequency components in them. The resonance of the whistle at the modes amplifies the fluctuations at the acoustic mode, which you hear as a musical note. When the slide is out, the tube is long, the wavelength of the mode is relatively long, and the whistle produces a low frequency tone. When you move the slide in, the wavelength gets shorter and the tone becomes higher. The penny whistle behaves like an open duct with a variable length. The fipple counts as one open end, just as with the slide whistle. The other open end is set by the position of the open hole in the penny whistle. So if I cover up all of the holes except for this one, this will look like an open condition. The duct to the right of this point becomes unimportant. So by uncovering holes at different locations along the tube, we can change the wavelength of the standing mode in the tube. For example, with this hole open, the standing wave will look like this. Its wavelength will be twice the distance between the fipple and the open hole. If I change the position of the open hole to be closer to the fipple, the wavelength shortens. This corresponds to a higher frequency, so the tone here is higher. This is the fipple of the penny whistle. As with the slide whistle, the fipple causes pressure fluctuations at all kinds of different frequencies when you blow into this end. The whistle amplifies the pressure fluctuations that are at the mode frequencies, so you hear a musical note with a frequency corresponding to the resonating mode. The mode shape, and thus the note that you hear, can be changed by changing the length of the tube by covering different holes in the whistle. When the open hole is far from the fipple, the tube is long and the wavelength of the mode is relatively long. The long wavelength corresponds to a low frequency tone. Opening a hole that's closer to the fipple decreases the wavelength and the tone becomes higher. Finally, let's take a look at the difference between the two types of whistles. First, let's take a look at a slide whistle where the slide is a distance L from the fipple. In this case, the first acoustic mode will have a wavelength that's 4 times the distance. Let's compare that to a penny whistle where the open end of the whistle is a distance L from the fipple. In other words, the open hole of the whistle is the same distance from the fipple as the closed end is for the slide whistle. The first mode of the penny whistle under these conditions will have a wavelength that's 2 times the distance between the open hole and the fipple. This wavelength is half as long as that of the slide whistle. Since shorter wavelengths correspond to higher notes, the note from the penny whistle should be twice as high as that of the slide whistle. If I blow into the slide whistle, the measured frequency is about 310 Hertz. Now if I blow into the penny whistle, I measure a frequency of about 660 Hertz. The slide whistle frequency is about half of the penny whistle frequency, which is what I'd expect, since an open-closed duct wavelength is twice that of an open-open duct of the same length. A penny whistle changes the wavelength by uncovering specific holes. The shorter the wavelength, the higher the tone. A slide whistle also changes the wavelength by moving a piston with this slide. As with the penny whistle, a shorter wavelength gives a higher tone.